In this short video, we'll have a quick sneak peek look at James Clerk Maxwell's distribution of molecular velocities for gases. The equation is a Boltzmann-style equation. The derivation is pretty simple, but most people don't need to derive it to use it, and at the general chemistry level, there's just a couple of proportionality features that will get you where you need to go, and that'll be the focus in this video. So essentially, I'll draw the graph and then we'll look at the equation and then we'll tease out the key features of the equation. So if you have a function of molecular velocities, so it's a function of velocity, and we can have population down here. No, we won't actually have velocity. So velocity down here, which makes a lot more sense. So we have velocity, and then we have a function that depends on the velocity. So I have a couple of diagrams that I should probably stick to here. So I'll make sure I hit my speaking points. Let's have a distribution at some temperature T1. Let's have another distribution at a temperature T2. And just for comparison, let's have a third distribution at a temperature T3. And here I'm assuming that T1 is less than T2 is less than T3. Okay. Now, I don't know how good of a job I've done. In fact, I've done a pretty abysmal job with this diagram. I'm actually going to erase my diagram because the key thing I was going to show you, I don't think I've shown you the way I drew that diagram. I was trying to show you the asymmetry of the plot. So I will try a bit harder this time. Velocity. I'm trying to show you that the right side is larger than the left side. So this is not a straight Gaussian. That's what I'm trying to show you. So if I were to put a mirror image right in the middle, it's asymmetric. There's more area to the right of the peak than to the left. That's what I'm trying to show you. So T1 that's a bit better. T2, and for the title, okay, a little bit better. Okay, T3. Okay, we'll put T1 back where it should be. Okay. Now, if I go to the absolute top and then just go to the right a little bit, so just off center to the right, these red labels would be VRMS, which in a previous video we saw was the root mean square velocity. So 3RT over m square rooted. There's different types of velocity you can look at. The average velocity, the root mean square velocity. I'm not really interested in the distinguishing and differentiating between them here. This is the one that we'll need at least at this introductory level. So we're going to consider these three temperatures and what Maxwell had to say about them. And essentially, without deriving the equation, which is pretty simple once if you have a look at the derivation, and I will probably upload the derivation notes to my students. So we have a factor of 4 pi because we have a spherical sphere of gas. Remember, a gas can expand in its container in any direction. We have a molecular weight. We have a factor of 2 pi RT. This is raised to the 3/2 power. We have a velocity squared. So that's our coefficient, and then we have an exponential decay function because it's an exponential decay function. So it exponentially decays e to the negative molecular weight v squared over 2RT. So that's Maxwell's equation. But really the important things for us in an introductory or general chemistry class are the fact that this function, to understand this function, I really don't need the constants. If you get stuck with what do the constants mean, you probably don't appreciate the constants. Just make the answer better. But the function, if we take the constant of proportionality away, it's proportional to mass and temperature as a ratio. So I've got a coefficient that has a mass and a temperature in, and then I have an exponential term that also has mass and temperature. So that's what's important. I'm not really interested in the 3/2 power. This is the important stuff. And whereas you can understand the derivation and maybe even memorize it, I think more people could probably memorize this relationship. M over T is a coefficient, M over T is an exponential decay. Okay, so let's see if we can see this equation in our plot. Well, first of all, let's look at temperature because that's what we have. We have temperature as a denominator, so I can see that the function is proportional to 1 over temperature. So as the temperature increases, the function should decrease because there's an inverse relationship there. So as the temperature increases from T1 to T2 to T3, as the temperature increases, the height registered by this function gets smaller and smaller and smaller. And that's this relationship here between the function and temperature. Notice also that as the temperature increases, the slope here gets shallower and shallower and shallower. So we have a steep slope at a high temperature, the decay here, a mediumly steep slope here, and then a most shallow slope here. Let's look at this exponential decay. Well, period, there's a slope, a decaying slope because of this exponential decay over here that has temperature as a reciprocal temperature in it. So as we increase temperature from T1 to T2 to T3, the temperature increases, so this gets smaller and smaller and smaller, and it is a decay, so the decay gets smaller and smaller and smaller. As the decay gets smaller with raising temperature, so the slope gets shallower with raising temperature. So that's the key interpretation of Maxwell's equation for temperature dependence. Let's go ahead and look at the mass relationship now. If we plot the function here, Maxwell's velocity function against velocity. Let's do the same for mass. I'll just do 2 of them this time. Let's let's call this M1 and M2. So here we've got M1 is less than M2, where M just means molecular weight or molecular mass. So let's interpret this just as we did for temperature. So we can see here that as the mass increases, and I've got those flipped the wrong way around. M1 is larger than M2 because M2, large things have a lower velocity and smaller things have a high velocity, so that would make sense that way. Notice I've tried to draw the graph asymmetrically, again with more area under the curve towards the right of the apex. Notice also as well, I didn't mention this, the area under the graph can't change. That's why broad areas get shorter, because it's a function of population. As long as your population hasn't changed, the area is your population, the area can't change. So that was an important oversight, but now we've overseen it. Okay, so here we have mass interpretation. The function is proportional to mass. So as the mass increases, so from M2 to M1, the mass increased, so the function got larger. So that makes sense. Also, if we look at mass in the decay here, as the mass increases, the mass is proportional to a decay, so the slope would increase with a greater mass. So the slope of the greater decay of mass 1 is greater than the slope of the lower mass M2. So again, we've looked at temperature interpretation, mass interpretation, both using the important features of Maxwell's equation, and this is what you can expect to interpret on an assessment in an introductory chemistry class or a general chemistry class. Next, we'll turn to the mean free path of a gas and the concept of Brownian motion, so a gas moving because of macroscopic collisions or microscopic collisions that would lead to macroscopic mixing, etc. So we're going to consider two gas atoms, but rather than consider just two uniform gas atoms, so instead of two gas atoms touching each other, so two spheres, here they represent gas atoms, each with a mass m. Let it be, we're essentially going to assume the same setup, but we're going to exaggerate it so that we have all the mass in one location and then a point source. So we've still got two masses, but rather than the realistic case, we're going to simplify the mathematics by assuming we have all the mass in one location, and then we just have a point source for the extra one. So this is our extra m over here, a negligible mass m. So instead of having a diameter of our system here, we're going to assume, well, I guess instead of having, if I do it this way, now the whole thing is trapped in that big M there. So D here is diameter, twice the diameter, or you could have the regular diameter there. Okay. So just to orient you with our assumption, and the assumption is just to simplify the mathematics. So over time, imagine that this large object carves out a tube. So let's say we take our big twice m, and over time it carves out a tube or a cylinder when it travels a length L, where L is its velocity multiplied by the time traveled. So again, over time, this object here is going to carve out an object, and I'm interested in how far it moves before it collides with a negligible point mass, m. So it really depends on how many m's you have here. So let this volume here, clearly we have a cylinder. It's in a straight line, we're assuming straight line motion. And the mean free path essentially is the distance traveled before it collides with m. So it would be this subunit of length here, L, until it hits something. So essentially, when you calculate the mean free path, you're asking, how far do I travel before I hit something, and then change my linear momentum. Let the volume carved out by the cylinder, V, equal, well, the volume of a cylinder is going to be the area of the circle multiplied by the length, because volume is area times length. So if you remember your grade school math formulas, the area of a circle is pi r squared. So here I've got pi. Now I didn't use r, I used d to be the radius. So remember, this is 2d, so I know that the radius is equal to just 1d because the radius is half the diameter. So if the whole thing across the diameter here is 2d the way I've defined it, then the radius would just be d. So pi d squared, or pi r squared, that's the area of this circle, and then I've got to multiply it by the length to get the volume. But the length is v dt. So that's the volume. So the number of collisions that occur in this volume are going to be scaled by n per unit volume times by the volume in particular, which is pi d squared v dt. So if you consider, I'll put it in parentheses so it's clear. So this is just our volume here. So in effect, the volume could cancel here. Then I've just got a number, which is what I want, a number. But I've normalized it per unit volume, and then I've scaled it to any volume I have. So the mean free path is just the length of path traveled during time delta t divided by the number of collisions during the interval delta t. So that's our mean free path. It's the length of the path traveled during the time divided by the number of collisions. So we can see that the mean free path is the length traveled. Well, that's going to be v delta t. That's just our length traveled, divided by the number of collisions. that occur, which is just this, because the volume here is going to cancel this volume and we're left with number. So we have n over v. So let's put it here, n over v. And then we have pi d squared v delta t. Now this is approximately equal to, and I'm going to say approximate because strictly this velocity and this velocity are slightly different. The details are not important to our discussion though. So the delta t can absolutely cancel. The velocities can approximately cancel. So if we take that approximation, this is approximately 1 over pi d squared n over v. So again, these velocities approximately cancel, but not exactly. So we have an expression, an approximate expression for mean free path. To make it exact, I'd have a factor of root 2 in there, but the details are not worth it for us. Okay, so this is good, but we need to go a little bit further. We'll incorporate some other concepts and we'll see ultimately how Einstein was able to use this concept to quantify Avogadro's constant. Okay, continuing on. So in the previous slide we saw our expression for mean free path, so the distance traveled before you hit something in the ideal gas state. Lambda, the mean free path, is approximately 1 over pi d squared n over v. So let's continue with that discussion. Let's assume ideal behavior. So if we assume ideal behavior, so remember we're assuming an ideal gas, then we can write the ideal gas equation and not be bothered by the van der Waal equation. Then we have PV is n kt, where n, we should probably use an uppercase N. We could use nRT if we like, but we're going to stick to one object rather than a mole's worth of object. We just don't need the added complication. So PV is nkt, and that will allow us to solve for n over v. So this means that n over v, if I bring the v over here, that's equal to p over kt. Where remember, k is Boltzmann's constant, T is Kelvin temperature, P is pressure, N is number, and V is volume. Recall that the product of temperature and Boltzmann's constant is an energy term, a classical continuous energy term. So that's nice also. It's always good to have an energy term in an equation that involves energy. So instead of n over v, let's write this. So this implies that the mean free path is 1 over pi d squared p over kt. Now notice that the kt is a double denominator, so it's going to wrap around to make a numerator. So that's going to be kt over pi d squared. So we've got our mean free path. Crucially, we can see the mean free path is proportional to energy. So that's a nice observation. And we could extend this to look at some of Einstein's arguments about mean free path, but that would probably be more appropriate in another video. I think what's important for us to know now is it allows us to solve for k. So measurement, I would say the big take-home message here, measurement of lambda permits calculation of Boltzmann's constant. We could solve for k. K we could say is mean free path over temperature multiplied by pi multiplied by d squared. So we could solve for Boltzmann's constant. And once we have Boltzmann's constant, we can recall something we did when we looked at gases. Recall we said that nk is nr, where n is total number of objects, k is Boltzmann's constant, n is moles, and r is the ideal gas constant. So for 1 mole, so for n equals 1, then Na, so if mole is 1, we're talking about Avogadro's number of objects. So NaK equals R. So Boltzmann's constant is the ratio of the ideal gas constant and Avogadro's number. The ideal gas constant is easily produced from a basic gas experiment. Mean free path can be measured from Brownian motion. And essentially, if you look at this equation, everything in here, doesn't matter which one you look at, everything in here can be measured, and therefore Boltzmann's constant can be calculated. Or, if you think of it from another point of view, we can solve for Avogadro's number. So Avogadro's number, to quantify it, would just be the ratio of the ideal gas constant over Boltzmann's constant. So essentially, once you have K, you can solve, once you use the mean free path equation to calculate the Boltzmann's constant K, you can sub it in here to the ideal gas equation and numerically quantify Avogadro's number. So this is important. Avogadro's number is not a convenient amplification tool. It's actually a real quantity in the universe.